thanks for coming. My name is Bill Spry, and I am a technical marketing engineering technical leader on the firewall threat team. So I work on all the kind of threat /Talos /AI related components of firewall. I also work on Live Protect, and have with me
Andrew Blunk. Everybody calls me Blunk. I'm a principal security research engineer inside of Talos. Show of hands, people familiar with Talos? Yeah? Oh, awesome. Nice. Okay. Yeah,
mostly because it was in the title of the abstract.
Why you gotta rain on my parade, Bill? Why you gotta do that to me, man? It's not cool. I do have a question for people, and this is really important before we get started. So, in the previous Cisco Live, I got dinged on my session responses because I was throwing snorties. Can we collectively agree that if we are sharing snorties, if they go off target, you guys will not hold me responsible and give me a 4-star? Can we collectively agree that?
I believe the quote in the response was better work on your throwing arm.
Yes, that was the quote, and as a result of it, I missed Distinguished Speaker in Amsterdam, so I am quite salty about this.
But it's probably like the best reason ever to miss. So.
It is.
Yeah. So a couple housekeeping items, if the clicker will work, here we go. You've probably heard this at every session, but we, like everyone else, have a WebEx room in the WebEx app. I think most of you are just kind of like automatically added to it, but Blanc and I will be in there for at least a month answering your questions. I think I'm in like 10,000 WebEx rooms by now, and I will probably be in here until I retire or whatever.
That's it. You got to step up your game, yeah. Man.
So you can probably reach us until the end of time in this WebEx room. Here is our agenda today. So the way I like to think of it, we're going to talk about kind of artificial intelligence / machine learning. You almost have to use AI now to make sure that it is search engine optimized. But we are going to basically start in the firewall, and as I like to think of it, work our way back, eventually behind the curtains at Talos. But everything we talk about is going to be a machine learning technology that the firewall directly benefits from, and for the most part with direct integration from Talos themselves. So, sounds good? We have a whole bunch of snorties because we have Blanc from Talos, I think, filled his entire carry-on bag with snorties.
It was so,
please ask questions. I think each question earns you a snorty. We also have some pretty cool stickers up here. My favorite is this snorty as like a vampire in this coffin. So some pretty cool Talos stickers. Those are always, I think, a little more fun and enticing than the Cisco ones.
Only vampires loathe light more than Talos engineers do.
So the first thing we're going to talk about is the visibility problem with TLS. And I guess I didn't say it, but to kind of frame it, we're going to show how different machine learning technologies we've implemented solve different problems in our product or in threat research broadly. So the visibility problem with TLS. So I assume most of you are familiar with some of these challenges, given that I assume a lot of your firewall engineers are familiar with firewall technology. But encryption is everywhere, right? We could show you a graph, and it would show that, right about 98, 99% of all web traffic is encrypted these days. Linux notches it down a little lower. I think some of the OS repos and stuff might still use plain text, but really it's almost 100%. So when you have encryption at 100%, and you also have your threat actors adopting encryption thanks to things like Let's Encrypt and other technologies, and the fact that it's so easy to do encryption now that it becomes kind of the default mode, even for the bad guys. How do we find those threats? Encryption passes right through the firewall. If your snort engine sees an encrypted flow succeed, it literally sends a message down to Lena saying, I'm done with this, it's encrypted now, you can just let it through. So threats get through that were once caught, and we can also decrypt and re-encrypt. And by the way, I do recommend that everyone have decryption as part of your strategy. But even if you are decrypting, some people have to wait because the box they're already running maybe isn't scoped to handle that overhead, so they got to wait until they refresh. And how many of you here are decrypting in some fashion? Excellent. How many of you, with your hands up, keep them up, are decrypting 100% of every packet going through your network? All right. Thank you, your attorneys and legal counsel, thank you. There's certain things you're not going to decrypt, right? Banking, healthcare, finance. You have things like cert pinning that's going to break or be let through without decryption, your choice. And then there's just other stuff that people choose not to decrypt for various reasons. So decryption's not always possible. We developed over the last several years what's called the Encrypted Visibility Engine. It launched in 7.1, I believe, on our platform. So that would have been 4 years ago, something like that.
Probably 5 at this point.
It's built on some of the fundamentals of an earlier technology called encrypted traffic analytics. But unlike that former technology that came from our stealth watch kind of era, Encrypted Visibility Engine is designed for decision making immediately. So it works on a number of different protocols. It launched with support for HTTP and QUIC and HTTPS/TLS. I just realized I haven't updated the slide, but in 10.1, which comes out here in a few weeks, we're adding support for SSH and STUN, 2 other encrypted protocols seen frequently in enterprises. What does this do? This performs analysis on your encrypted traffic. Now, we're not going to do the same thing that intrusion prevention rules do, the same thing that the malware engine does. We can't look into that stream magically. We haven't somehow cracked the code. But what we can do is use really big data, and I guess I'll skip ahead here, from a variety of sources. Actually, these numbers can bump up a little bit since last year. We're actually using about 150,000 endpoints today, per day that we're collecting telemetry from. I don't know about this little machine, but our laptops over there are certainly providing feedback into this. We have a number of customers that we have partnerships with that provide telemetry. And what's cool about our endpoint telemetry, anyone familiar with NetFlow? Anyone want to just someone speak out? What is NetFlow?
A record of every conversation with the 5-tuple.
There you go.
The addresses and what ports.
Yep, absolutely. So NetFlow normally comes from a router or a switch, something like that. Firewalls can send NetFlow too, technically. There's also this concept of enhanced NetFlow that some of the Catalyst gear can do, which adds a few other properties. Our endpoints can send NetFlow using Cisco Secure Client and our network visibility module. And there's a really unique thing that's pretty cool in there that's useful for big data and machine learning, like model training, which is we append the process name to every flow sent. So we can label, it's labeled telemetry. We see this client hello, we see this communication, we see these destinations and ports, and we know it's this process because it literally is saying from the endpoint, it is this process. So that's labeled data. We also have, it's actually over 2 billion unique TLS fingerprints per day we're gathering now. So much more than that in total fingerprints, but unique over 2 billion per day from different data centers and other warehouses that we're able to collect them from. And that's unlabeled telemetry that we can add into the pool. And then we also run Cisco Secure Malware Analytics, which we have about 10,000 net new malware samples detonated in there per day. And so we take all of this into our big machine models, our data mining models. They go via the vulnerability database, which also sends app ID and some other stuff to your firewall. That now sends encrypted visibility engine feeds. And we are running on the firewall a naive Bayesian classifier model. That is a model type. It looks at every flow coming in of those types, HTTP, HTTPS, QUIC, STUN, and then in 10.1, STUN and SSH added into the mix. And it says a few things, but it first and foremost says what process is this likely to be, and how confident am I that it is this process? And it looks at some initial clues that precede the encryption. So for the classic example, HTTPS, it's going to look at the client hello packet. It's going to look at all the different parameters that are contained in there that can be read right on the wire because it's right before the encryption happens. And what we found is that there's really unique collections that we can use and hash different parameters of the client hello packet to essentially classify it. And then we look at where is it going? What's the destination IP? What's the destination port? If there's an SNI or a domain that I've cached through DNS snooping, what is the host that it's going to? And with all of that combined, this model will assign a process identification. Hey, this is Chrome, this is Safari, this is Firefox, and it gives a process confidence score. If the score exceeds about 90%, I think it is, it will actually map to your app ID, which allows your app ID engine to be more effective because the app ID engine has traditionally often relied on deep packet inspection. So it bolsters that, but from a threat standpoint, because we are here talking about threat stuff, it also assigns a threat confidence score, because some processes are malicious processes. That NJ-RAT Trojan running on your endpoint that you're infected with is a process that's running there. So that's part of the process identification. So we also assign a threat confidence score, and on your firewall and your access control policy, you can say, turning on what's called protect mode, and you can set a threshold of high or very high and say, when you hit this threshold of threat confidence, go ahead and just block that connection for me. And even if you don't do that, we're gonna log the threat disposition and log the process name. All of the things that we believe are malicious, we append or prepend with the term malware, so it'll be like malware-njrat, malware- I don't know all the names offhand, but it'll be whatever the malware family we think it is, or if it's an unknown or a generic one, we'll give it a more generic kind of name. But that's all based on a machine learning model that's running directly on the firewall. And here's an example kind of to illustrate the point. The Tor browser, the Onion Router browser, is built off of and kind of forked from the Firefox open source project. So in a lot of ways, it looks pretty similar. And our firewall today, by default, will just classify both of them as like SSL client. It's a generic app ID disposition. If you turn Encrypted Visibility Engine on, we start looking at the TLS client hellos they make, and they are notably different, and where they're going is different. The Tor browser, as you may be aware, goes to a very limited set of things as its first hop. So from the vantage point of the firewall, it's not going all over the internet, it's going to whatever the first node is of the Onion Router network. And thanks to the Encrypted Visibility Engine, we will then differentiate, for example here, between Firefox and the Tor browser. Does that make sense? Yeah.
Is it firewall analyzing only just the beginning of the flow, or if it's the flow is giant flow, it analyze every packet?
Yeah, it's a good question. So the question, for anyone that couldn't hear, does it just analyze the beginning of the flow, or does it do like a continuous analysis of the flow over time? The answer is it does just analyze the beginning. So the example I gave with client hello is specific to HTTPS. To be honest, I forget what the parameters are in SSH and stun, but it's the similar type of initial packets that precede the encryption. But yes, we have to make a decision quickly. You could argue that you could block it at the end of the flow, but if you look back at a tool like a StealthWatch or Secure Network Analytics, it's kind of passive and retrospective by definition in a lot of ways. So it was built over like analyzing packet density and stuff like that. This is trying to make a quick determination. We want to determine by around packet 4 because that's around the length of time the traditional app ID engine has. It allows us to do rule disposition matching very quickly to make sure that we're doing things like decrypt or not decrypt still in time based on the app ID that you assign it to, all those kind of parameters.
So the first packet can pass through?
Yeah, if you're doing an encrypted visibility engine block, again, like for HTTPS, it's going to be packet 4 when it makes the decision to block or not block. So the TCP handshake would have gotten through still. Yeah. Any other questions on that? Yeah.
If you're going to cover this, no worries, but what's the performance hit on like a non-3100 series?
Yeah.
It's got the off-level capability.
Yeah, so the question is, what is the performance hit when you run the encrypted visibility engine? We don't have a hard number because everything with firewalls is different per entity. Everyone's mixture and stuff is different, but it's going to be low single digit, generally about 1 to 3% performance. So if you're not running your box at 90% already, then you should be safe to turn it on. Anecdotally, some of the super old gear, like the 1010, I've seen some people where that tends to be an issue. Like 220s, 1200s, 2100s, those are all fine. Yeah, even the I've run it for years on my 1140 with absolutely no issue and no perceptible difference when it's on or off. Yeah. Cool. So the next problem we're going to move to is the scaling problem with exploits. So does anyone know, let's ignore this year because it's still in motion, what year had the most CVEs ever disclosed? Anyone? Anyone want to take a guess? Huh?
2 weeks ago with
For the year. Which calendar year saw the most CVEs of any calendar year since the program started?
2026.
Well, let's ignore this year, but I'll still give you credit for that, 2025. And if we went back to January 1st, 2025, we'll give one more snorty out. It's January 21st, 2025. If I would have asked the question then, What year had the most CVEs of all time? Excellent. Everyone gets a Snorty.
No.
And you could basically rinse and repeat back in time, and that's the case. If you look on the charts, and there's different websites that track this, it is a like never-ending, like where is the ceiling on this thing? There are more CVEs year after year after year. And so we have Talos, which is a really great threat research team with hundreds of employees and a bunch of people writing snort rules and doing coverage. Blanc is probably not writing the snort rules. He's here at Cisco Live this week.
Not for the last 12 years.
But a lot of very smart people at Cisco that are doing it. But the problem is when you have more and more CVEs, we can't ramp up indefinitely and have infinity employees or whatever, 20,000 employees just writing snort rules. So we do a great job writing them, but we're also forward thinking. This doesn't scale indefinitely. And you have also things like Mythos that you've heard all the people on the stages talking about this week. But there are real concerns that this is going to keep growing. So it becomes hard to throw literally enough humans at the problem writing rule coverage. And no, we would prefer not to blindly have ChatGPT write snort rules for you. I've seen that, and you need a human in the loop.
We tried. It doesn't work well.
Yeah. So there's an increasing demand, at least that we foresaw, to get ahead of this holistically. And I always think back to my days doing SANS training. You get really seasoned at doing security analysis, and if you see a novel SQL injection attack, for instance, I know it when I see it. I don't know what specific exploit it was targeting. I don't know all the parameters around it, but this thing here on the wire is a freaking SQL injection attack, right? You know it when you see it. But Snort doesn't work that way. Snort is using different types of pattern matching and things of that nature, but in an atomic nature, right? So for instance, if I write a snort rule that matches on 1 equals 1, it's not going to match on 2 equals 2. So there's a constant need to keep writing these rules. And by the way, none of what I'm about to say means we're going to stop writing those rules. But we want to be holistically ahead of things. Get this to draw. Here we go. So henceforth, we came up with SnortML. And this is a pretty amazing tool. This, again, is on-box machine learning. We are running, in this case, a TensorFlow model. So you got Eve and SnortML bring 2 different machine learning models that are literally resident on the firewall. They run in an air-gapped network. Hey, I'm with the DoD, no problem. You can turn these on, and they will protect you, or your power plant that's air-gapped, whatever. SnortML is trained against millions of URLs. We use things like the common crawl set to train it on what normal, benign browsing traffic looks like. And then we have a variety of sources that we collect PCAPs of different attacks from. Guess what Talos has? They have a repository of different injection attacks and different types of attacks in PCAP form going back decades. And we have ways of synthetically generating that, et cetera, et cetera. So we have then trained models on entire vulnerability classes. So in 7.6, we launched support for SQL injection. That was our initial release. It can detect class-wide SQL injection attacks. In 10.0, we added support for command injection as well as cross-site scripting. And the kind of North Star goal is the OWASP top 10. There's going to be certain things in there that are not applicable to a firewall to detect. There's things like privilege escalation, things that maybe an endpoint would be more able to detect. But for everything a network device, like a WAF type thing could detect, we're hoping to expand SnortML into. So the idea here, kind of repeating the flow we did for Encrypted Visibility Engine. We train it on a bunch of Talos threat intelligence, a bunch of publicly available data. We train this model to know it when it sees it, right? And we deliver via the LSP. The LSP is the lightweight security package. Talos built that alongside Snort 3. If you're familiar with SRU, it's similar to that, but the Snort 3 version of that. So your firewalls are able to check for daily updates if you want on that, and I advise that. If we have kind of Delta model updates to deliver, those get bundled right into that LSP you're already installing, and the TensorFlow model is updated with new detail. So we see an incoming traffic flow if that model is on, and in the case of HTTPS or QUIC, we want to make sure encryption or decryption is on for that inbound flow to your server. We are going to look on our TensorFlow model and say, hey, is this SQL injection? Is this command injection? Is this cross-site scripting? Yes. Let's block an alert. No. We'll let it through. There was a question about performance impact. I'll mention, just getting ahead of that. And I think it's 10.5. We are making this
10.1.
10.1, we're making this on by default in our security over connectivity policy, which is the second most used base policy that we see amongst our customers. Today in 10.0 and earlier, it is only on in max detect by default, but you can turn it on. You go into your rules and configure it as enabled, and it will turn on. The performance impact, on average for a flow, it's down to about 15 microseconds of added latency that we do, which is pretty awesome. And this is running a full TensorFlow model inline, at line rate speed on a firewall, which I think is amazing.
On the CPU. No hardware acceleration. On the CPU.
Yeah, 15 microseconds. The way that we've achieved that is we have activated certain memory conditions. So if we see identical flows, we're able to quickly classify those. We've built in some smart pre-classifiers so we can identify things that are impossible to be any type of attack and get those out of the way. And that gets us down to that 15 microsecond number, so it's pretty amazing.
Bill, before you go on,
Yeah.
or before we move on, can you go back to the slide? One of the really interesting things that I want to talk about as it pertains to SnortML is, you know, as we pivot out of like signature-based detection models and into stuff like machine learning, it empowers us to get more proactive about the detection that we're authoring as opposed to reactive, right? So like, the traditional model for IPS signature generation is, okay, a vulnerability gets disclosed, it gets weaponized, right? We become aware of it either at disclosure time or maybe a little bit before, depending upon circumstances, or we become aware of it at weaponization time. But like, that's when the clock for us starts of crafting IPS rules. But like, the clock for the malicious actors started the moment they realized that the vulnerability was there and it could be exploited, right? So crafting signatures is always going to be reactive in nature, right? SnortML breaks that model, allows us to get a little reactive, or I'm sorry, proactive. Do you guys remember React Shell vulnerability from last year? Yeah. Okay, so if you go back a couple of years, the time delay between vulnerability disclosure and weaponization of an exploit was measured on the order of like 2 months. And over time, we've seen that come down. In the last 2 or 3 years, we've seen that accelerate rapidly. Would anyone like to hazard a guess as to why? That is correct, right? It's a tool. Helps you find things, helps you weaponize things. The time delay between vulnerability disclosure and weaponized exploit for React Shell. Would anyone like to hazard a guess on that? 5 hours. 5 hours.
Does anyone patch their firewalls in 5 hours?
Okay.
Man, I'm the only
Now,
one.
why am I talking about this? Fun fact, React Shell is a command injection attack, right? Okay. So as soon as React Shell dropped and we have a weaponized exploit, we were like, okay, let's go create our snort rules for this. But hey, this is command injection. Let's go check this against SnortML. Blocked. Right out of the gate. We didn't have to retrain a model. We didn't have to do anything. SnortML was already blocking it. Yes?
Is this an input for Live Protect?
No, this is unrelated to Live Protect.
So yeah, Live Protect is about protecting Cisco infrastructure, right? So it's, hey, our firewall has a vulnerability, therefore we want to put a shield in that to make sure our own product we sold you doesn't get owned or exploited. This is leveraging machine learning, so it's a different mechanism, but this is about protecting your assets. If you have a device susceptible to Log4j, you've got a vulnerable WordPress server, whatever it might be, that's not us that caused that vulnerability. But we want to be the device that helps protect that vulnerability from being exploited on the wire. So that's where SnortML comes in. Yeah.
To implement SnortML, you mentioned it's available in 7.6. Do I go to my ACL and advanced settings, or is it a security?
It is an intrusion policy.
Yeah, the intrusion policy. It's not exactly a clean way to turn it on, but it's through the intrusion policy and the network analysis policy. So like, you have to make 2 changes in tandem if you're trying to turn it on in one of the lower security policies. You do have to be a little careful there because the performance optimizations that Bill talked about, right, about like pre-classification of the traffic before we actually do the machine learning based detection on it, that all came into Snort core engine at a later version. So if you turn it on in those earlier versions, yes, it exists, but none of those performance optimizations exist. So like, you will experience some performance problems there.
There's one thing I'll throw though that kind of balances that a little bit, which is you do have the ability, just like you can make different firewall rules or access control rules, you can make different intrusion policies. So if you're like, hey, I have these public-facing servers that I really, really want this for, but I don't want my outbound web traffic to hit latency on its inspection, you can kind of clone, or you might already have different intrusion policies. You add it to the one that's targeted only to your inbound DMZ, and that's the one that's going to have that increased latency, which a lot of people, I think it's closer to 300 microseconds, so it's not like an insane amount of latency there. And a lot of people would say that's acceptable for this kind of vulnerability class coverage for these specific important servers.
And for the increased efficiency, that was 10.1?
10.
I think it was 10.0 that did the latency
yeah.
improvements, but 10.1 is when we'll just make it default in that security posture for you. Yeah.
Good questions.
Yeah. I'll hand it over to you, sir.
All right. So Bill has kind of talked through how machine learning is getting leveraged within the firewall, like so we're on device, right? Now we're going to take a step back, pierce behind the curtain inside of Talos, and start to talk about how Talos leverages machine learning behind the curtain to drive everyday detections on the firewall. So first, we're going to talk about the scaling problem with malware, right? And we have a very similar challenge with malware that we have with exploitation, right? It's pervasive. There are new malware samples appearing every day. And in the same way that we can't throw enough bodies at the problem as it pertains to exploitation detection, we can't do the same thing with malware, right? Like, we're also not wizards. Like, I can't craft 500 million claim AV signatures in the space of an hour. It just does not scale. Additionally, there's an increasing demand for covering classes of threats instead of just doing atomic threats. So where does this kind of lead us? Well, it leads us in the direction of magic, which is auto-generated claim AV coverage, right? How many people here are familiar with claim AV? That's it?
Got a new hand that wants to say in a summary what claim AV is?
Someone who doesn't already have a Snorty. You already have a Snorty. Yes.
Yeah. See if I can reach.
You're getting a 4-star now. See, this is what I like about these sessions, is when we're all joking and laughing. Okay, so magic is auto-generated claim AV coverage, right? It works by sampling together malicious samples, clustering together malicious samples. It is AI and ML-driven creation of claim AV signatures, and it gives you the best of both worlds from a machine learning perspective and from an atomic coverage perspective. Let's talk about how this works. So magic will take the samples, and we will feed it to machine learning to generate sets of clusters, okay? Those sets of clusters will then be fed to more machine learning to actually generate the coverage. And that coverage is then going to be checked against the sample cluster that it was written for. And any sample from that cluster that it does not cover, what do you guys think we're going to do with that?
Put it back in the hopper.
Exactly, put it back in the hopper, right? Chuck it back in the hopper, and it's going to go through the process again, right? For the coverage that does make it through, right, we're going to false positive check it, and then we're going to shove it out the door and cover it. Now, the sample clustering itself, it's machine learning based. It leverages Detectron, or no, that's the next slide. Haha. So how do we cluster those samples? We're going to use Detectron 2, a residual neural network, and PaddleOCR. Why do you guys think that we use PaddleOCR for part of this? PDFs, okay. What specifically about PDFs? What kind of information would you have in a PDF that may indicate maliciousness that would have utility in comparing against other samples? QR codes, yeah. What is a QR code usually? A URL, yeah, exactly. Yep, you already have a Snorty, so you don't get no more Snorties. You're cut off. So yes, it's going to use artifact similarity, and the outcome of this is going to be, as I said, a cluster of samples that we can actually do detection engineering work on. Once we've got that sample cluster, we need to reduce our data set. So we're going to take that sample cluster and we're going to carve out things that we do not need, right? So things that are obviously false positives, things that we already have claim AV coverage for, because if we already have coverage for it, no sense using machine learning to try and generate more coverage. Just don't waste our time processing those unnecessary samples. Don't waste our time, expending CPU cycles on things. The outcome of this is going to be, we've taken that sample cluster and we've now broken it down by file type to feed to additional learning, machine learning. Now we're gonna auto-generate our coverage. It's magic. What's the machine learning in play? It's gonna use hill climbing. Is anybody here familiar with hill climbing? No? Okay, so hill climbing is a flavor of machine learning that has to do with optimization of generating some type of a result where any further iterative tweaking of the signature does not yield a further benefit in terms of detection, right? So you basically want to iterate on that rule until you reach the peak of coverage, and any further tweaks to it, no matter where, it's an unstable equilibrium, and any further tweaks is resulting in less things that are covered. Once you've climbed that hill, that's going to be the signature that you're proposing. Now, once we have that proposed signature, rarely do we have one signature that detects the totality of the sample set. So we need to take that, we need to run ClaimAV using that signature against the sample cluster, and anything that's not alerting, we're going to carve out of the cluster, and we're going to re-inject it back into the bucket, and then we're going to start the process again on that bucket, right? And this just flows through until we have generated all the ClaimAV coverage that we need to. Once we've got that, we never YOLO it out the door. Never go full YOLO when it comes to coverage. We've learned that lesson many, many times. So those signatures have to get false positive checked before we release them. And assuming that they pass the false positive checks, then it's going to go out the door. Now, what I'm describing here is ClaimAV signature creation, and that's cool, right? Like antivirus. What's the value add to you guys from a firewall perspective? Well, let's say I've got an unknown file, and I have a secure firewall with a file policy where local malware analysis has been enabled. And I've deployed that in an access control policy down to my FTD, and FTD is observing network traffic, and it sees a file, right? Carves that file out of the network stream, and it's gonna go do an evaluation against it. Fun fact, local malware analysis uses what? ClaimAV, exactly. So that auto-generated ClaimAV signature, right, the impact for it is we can generate a malware event on FMC. It's atomic coverage, it's deployed to your FMC, right, but it's machine learning based. The source of it is ML, but it's still atomic coverage running on your device. That's great. This is an unknown file. It requires a malware license. There's another pathway for this, which is if I have my file policy and I've elected to use dynamic analysis, I deploy my access control policy, FTD is chugging along, it sees a file, carves the file out of the network stream, right? Goes and takes that sample, does a disposition check to the the malware cloud, we call it?
Yeah.
Malware cloud. Gets back into unknown disposition, right? And you guys have elected to use dynamic analysis. It's going to take that sample and it's going to submit it up to secure malware analytics for detonation in the sandbox environment. Secure malware analytics, there's a lot of stuff that happens in there. Would you guys like to hazard a guess what one of those things is? Scans it from ClaimAV, exactly. So again, machine learning driven atomic coverage going into a detection capability. Now, secure malware analytics comes back and says, well, this is a malicious sample based upon this ClaimAV signature run, right? What you'll get is a retrospective malware event on the FMC, okay? Now, this file, what do you guys think that we do with it once we've identified that it's bad? Pardon me? Send to Talos. I mean, that would be a good idea. Then we don't. Yeah. But what do you guys think we do with that hash?
It goes into the query cloud.
It goes into the query cloud. So now we've got an impact for a known file, right? File policy, dynamic analysis, right? Oh, the slide is a little wrong. It should say malware cloud lookup, my bad. But we deploy that to the FTD. Firewall is observing network traffic. It sees a file, carves it out, SHA-SUMs it, submits that up to the cloud, gets a disposition. This is malware. Now I've got a malware event on the FMC. So that same set of signatures can produce a malware event on your FMC using 3 different mechanisms. Directly on the device using local malware analysis, indirectly and retrospectively using a submission up to secure malware analytics, and directly based upon the poking of that sample to a malicious disposition once we've identified it.
So I'm curious, if secure malware analytics finds that it's malware via a different mechanism, does that potentially feed into Magic as something in the hopper?
If secure malware analytics identifies something as malicious, will it feed into Magic?
Is that one of the sources of the Magic process?
I don't know the answer to that.
Sorry for stumping you on the spot.
Yeah, I don't know the answer as whether it feeds into Magic. I do know it feeds into a different ecosystem, which is called Gravity. We don't talk about Gravity in this discussion, but the whole point of Gravity is to basically take detection names and repoke them to something that actually makes like sense to someone. So how many people here run firewalls with file policies with like malware cloud lookups? Okay, so when you see the detection name, right, you guys know like, oh, w32.a32468, whatever, .sbx.tg, right? Like, okay, cool, this thing is bad, but I don't know what that is. Gravity is a program that takes that and will turn it into something like, that's Ghost Rat, or that's WannaCry, or that's whatever. Gravity is basically a tool that we have internally to repoke samples, and we've trained it on, I don't know, maybe 40 to 100 different malware families, but that's outside the scope of this discussion.
Yeah. Yeah.
Is FTD acquiring cloud itself, or it's going through the FMC?
FTD goes directly.
Yeah.
And
Yep.
what we just discussed is all applies to unencrypted or decrypted traffic.
Well, it depends upon how you've configured your FTD to operate. If you're doing decrypt and resign, then Snort has a capability to carve out those files. If you're not doing decrypt and resign, then you have an L3, L4 firewall with app ID and encrypted visibility, and that's about it.
But although, yeah, in certain, like SMB v2 is still prevalent, they're still definitely inside of an enterprise.
Yep.
But yeah, to answer your question directly, yes, it has to be either plain text traffic or traffic that you've decrypted either on the firewall or on something like a decryption appliance around the firewall.
Yep.
Yeah.
Any other questions? Yes?
Where you say FMC, I'm assuming that's also security cloud control as well.
Yes. Yeah, the management, the firewall manager.
Do you guys through here have any places where it's not true? Call that out.
Yeah, so policy management of FTD through security and cloud control under the hood, and keep me honest here, it invokes the CDFMC UX, I believe.
Yeah, so I'm thinking through everything that we're talking about today is available whether you manage in cloud control / security cloud control or whether you manage in an on-prem FMC. So yes, it's all available through cloud management.
Anything else before we move on? Okay. All right, next challenge that we are going to talk about is the scaling problem that we have with web categorization. Are any of you guys using the web categorization capabilities on firewall through the access control policy? Yep, URL filtering, exactly, yep. So obviously, web is a pretty important vector, and there's a need for acceptable use policy enforcement. Deep packet inspection on the firewall is computationally expensive, so we want to be able to block as early as possible get the flows, either allowed or blocked as early as possible, computationally inexpensive as possible, before we actually have to spend CPU cycles and memory doing stuff like DPI and file carving and SHA-summing and stuff like that. So this is where web categorization kind of enters the chat. It's the categorization of HTTP URLs. We support multiple languages. Last check, it's 40 different languages that we have support for. It's AI, ML-driven categorization of the URLs, and it supports lookups back to Talos with dispositions and answers at line speed. How does this work? Well, we're going to take our URLs, we're going to feed them into a crawler, and we are going to feed the artifacts and the HTML that the crawler generates of those URLs into a content analysis engine, covering those 40 different languages. For every single one of those AUP cats, the content cats that you guys are all familiar with, there's a different model for each one of them, and 40 different subvariants of those for every single language that we support. The ultimate output of this is going to be the content category that you guys are using in your access control policies. Either say, yep, you know what, I want to block pornography, right? I want to allow finance. I want to block, terrorism. I want to allow healthcare, right? Yeah.
How is the firewall getting URL from DNS query, or it's
So the way that firewall is obtaining the URL, well, what gets queried back to Talos using web filtering can come primarily from the HTTP URI, but I believe it can also grab the host name from a DNS request, and I believe it also looks that up.
It does. Yeah, that kind of quietly was added in 7.4 maybe, something like that.
Yeah.
if it's from HTTPS, it should be decrypted as well?
So it depends. If it's in an encrypted form, firewall has the capability to grab the SNI from the TLS handshake and to include that in the lookup.
Yep.
Obviously, looking up a host name is going to give you a somewhat different answer than looking up the fully qualified URI, right? Looking up drive.google.com is going to give you something vastly different than drive.google.com/this specific file, right?
Yeah. If you have encrypted visibility and engine enabled, something we didn't mention here, but another thing it does is it actually performs the mapping for quick as well to a host name as the URL, represented as the URL. So, yeah. And then that feeds the lookups.
So our first generation web categorization, and again, just a reminder, this is all ML based, right? First generation of this, 2008. So every time that people talk about, we're all in on AI and ML, we've been all in on AI and ML for, at this point, 18 years.
Does anyone know what organization that's now part of Cisco built this classifier model, the first gen? 2008, huh?
Umbrella? OpenDNS?
They were not around yet, I don't think.
Nope.
So no.
SourceWire?
Huh?
Nope, not SourceFire.
SurfSafe?
No.
Nope.
You're getting fun guesses. What is a product that we have that does URL filtering that's not the firewall that may have been around 20-ish years ago?
It was Ironport.
Yep. Who said Ironport?
Yep. It was
Who
Ironport.
said WSA? You get one too.
Another 4-star.
Yeah.
All right, so our first generation, 2008, uses a Bayesian classifier. Why a Bayesian classifier? Because in 2008, that was about what was available to us at the time. Right? Not going to mince words. Outcome of this, obviously, is just straightforward. This URL is pornography. This URL is guns. This URL is finance. This URL is healthcare. Our second generation of web categorization came around 2016, and it used the word-to-vec, long short-term memory modeling. Anybody would like to hazard a guess why we went with word-to-vec?
Does anyone know what word-to-vec is?
Cool. TLDR, performance and accuracy, right? It was faster, it was cheaper, and it was more accurate. But again, 2016, 10 years ago. Which leads us to our next generation web categorization, which we started building in 2024, uses auto glue-on, and also supports 40 different languages. Would anyone like to hazard a guess why we chose auto glue-on? Performance and accuracy, exactly, right? But the key takeaway with this is, again, we have iteratively worked on our accuracy, our performance, trying to do this at scale. And fun fact, anything that comes up in a query form to us that we don't know the answer to, that goes into a bucket. And what do you guys think we do with the URLs that are in that bucket? We feed it to the engine, right? It's the whole point. All right, so what's the impact for firewall? Impact is if you've got a web filtering license and, whoops.
Is this not the right one? Oh.
Yeah. Yeah, that should say access control policy.
Well, we'll just pretend.
Yes.
Yes.
Access control policy with URL. So you've deployed your access control policy to FTD. FTD is observing HTTP requests. It carves out the URL, and it goes and queries the cloud. Cloud comes back, says this is the acceptable use policy category. It's going to generate the event, and the outcome on your firewall is going to be a security event on your FMC dashboard. Any questions before we kind of move on? Bueller? No? Okay. All right, now we're going to talk about one of the really fun ones, and this is the scaling problem that we have with phishing. This is very near and dear to my heart. How many of you guys are worried about phishing in your environments? Okay, whoever is not raising their hands, you guys need to talk to your security officers, okay? All right, so we still have the same type of problems that we have with web categorization, right? Web is a vector, we need phishing prevention, right? We want to bail on things with block allow decisions way before we have to get into deep packet inspection because that's computationally expensive. We want to block as cheaply and as early as we possibly can. So how do we do this? Talos built an entire engine that we call Cloud URL Analysis. Cloud URL analysis is used to identify phishing and impersonated brands. It's driven out of lookups coming out of the secure email portfolio. And it is ML-driven analysis of unknown URLs, and we expose the results of that back to all Cisco Secure products. Why do you guys think that we why do you think that we drive this out of data coming out of secure email?
That's the biggest bound vector for attacks.
Exactly. Like if I have a URL and it's coming out of secure email and it's unknown, right? That's gonna have a little bit of a different connotation than just any regular old URL on secure firewall that has an unknown disposition, right? You guys are NetSec people and security people. Like you have firewalls that are protecting internal devices, right? Those internal devices are gonna have some web servers running on it on some RFC 1918 space. Talos is never gonna know what those things are because they're not publicly available. Like there's no way for us to give you an answer. So the data coming up out of secure email that's unknown, that's a really good intelligence source for us. So how does this work? Well, first we're gonna take those URLs and we're gonna feed it first to a convolutional neural network that kind of determines how fishy does this look lexically, right? Is it Bank of America where bank is spelled with a C and America is spelled with a K and like, you know, the E is leet speak, it's a 3, right? Does this look like it's trying to trick someone into thinking that it's one thing versus another, right? If the outcome of that fishiness detection is, yeah, this looks fishy, then we're gonna feed it to a crawler. And then the crawler is going to go look at the website. It's going to take all the artifacts off of it. It's going to take the HTML, any files that are there, and it's going to dump them into a bucket, and then we're going to process all of those artifacts through more machine learning and more detection algorithms. The culmination of all of this is going to be the URL is either being labeled as untrusted and it's phishing, or it's spoofing, or if there's any files, we'll mark them as malicious, in the malware cloud, and provide detection names. How does this actually work, right? So first, we want to find out, does this really look fishy, right? As I said, it's a convolutional neural network. The whole point of this is to kind of bail out early if the lexical analysis doesn't look like it's all that fishy, right? Again, we don't want to be wasting cycles. There's a great saying that one of my mentors used to say, which was that we could solve all the problems in the world if we had infinite compute, infinite money, and infinite storage. Unfortunately, we don't have those three. So we have to optimize in some way. So deciding whether or not something is fishy or not before we actually go through the steps to really, really take a look at it, this gives us an opportunity to bail out early. Once we've determined that it's fishy, then we're going to go crawl those URLs. And the purpose of this is to just assemble the data. We want to grab all the things associated with that URL, that page, that we could potentially do analysis on. This includes, like I said, the HTML or the files that are being pulled down. This also includes taking a screenshot of the web page as it would be rendered in your browser. Okay, well, let's park that. We want those screenshots because we're going to run it through an image similarity engine. And the purpose of the image similarity engine is to take those screenshots, hash them, and then compare them against a known corpus of other screenshots of known brands and known externally facing assets. Right? So you can kind of think of this as, we know what the Bill Spry's widgets brand looks like, and we know the externally facing assets of Bill Spry's widgets are these 17 different host names. So if I see a screenshot that has a hash that looks similar to Bill Spry's widgets and is not one of these enumerated hosts, this looks like phishing. Can't guarantee that it's phishing, but it looks pretty damn much like phishing. Okay? That's the whole point of image similarity. It's basically using our understanding of the computed hashes, and it's not one-for-one hash comparison. Obviously, it's fuzzy comparisons. But it is comparing those image screenshots of the web pages to a known corpus and cross-referenced with the externally facing assets that we know. We also do that for nudity detection. So those screenshots that we take, we're going to compute those hashes, and if those hashes look like it contains nudity, well, guess what? We're going to mark that site as untrusted and not quite phishing, but it's going to get labeled with the AUP category of pornography or nudity, depending upon circumstances. We're also going to take all of those artifacts that we consumed from the web crawler, and we're just going to do signature-based analysis on them, right? We'll run them through Yara, and the outcome of this is going to be, depending upon circumstances, the URL gets tagged with a threat level, it's untrusted. The URL gets tagged with the threat category, it's phishing, it's spoofing, it's malicious, right? And the file is going to get poked with a malicious disposition. The last part of this is something that we call codfish, and this is when good hosts go bad. So when we go to, oh, yes, there's a question.
It was just a question about the crawler.
Uh-huh.
What happens if there's a web page that's needing credentials or something like that? Does it actually put credentials in?
So currently, the crawler is not capable of handling web pages that require credentials. And again, this is all behind the scenes at Talos. So even hypothetically, if you did have those credentials, there's no way to share them back with us. Any other questions before I finish up with Codfish? No? Okay. So Codfish is when good hosts go bad. So let's say that I have managed to hide a malicious file up on drive.google.com, before Google is aware of it, and I start sharing that out. And I've got a URL, right? Fully qualified URL. This is a new fully qualified URL. There's no previous indications on it. It's unknown, right? Gets fed to Kua. Kua is going to hand it off to Codfish, and Codfish is going to go to drive.google.com and try to pull down that publicly available file if it can. If it can, and if it's a file, then it's going to extract those, and it is going to cluster that file with similar samples. Does this sound familiar? Yeah? Okay, we're going to take that file and we're going to re-inject it into the process that's doing something very similar to magic, right? We're going to use Detectron and residual neural networks and Paddle OCR to do sample clustering, and then we're going to feed it into another engine, right? So you can start to see the linkages between the back-end architecture and systems that Talos has. Our system for processing unknown URLs is intrinsically linked with the system that we have in place for processing unknown files. Yes?
Does this then all filter down to the firewall level as content rules?
So in the case of files that are extracted by Codfish and clustered and going through the magic process, then the injection point into firewall is no different than any other ClamAV signature. It's the same thing, right? Local malware analysis goes over to secure malware analytics, and yeah.
But from the URL stuff, the previous steps, that's all part of the URL content filtering.
Mm-hmm.
Yeah.
Rules
Yep.
that get pulled down by firewalls.
Yep. All right. So the impact for this, for firewall, is, again, this requires a web filtering license. You have an access control policy with URL reputation. You're going to deploy that down to the FTD. FTD is going to observe an HTTP request. It's going to go query the cloud. The cloud, in this case, is Talos. It's been fed by all of the machine learning on the URLs that it came up from secure email. It's going to get a disposition lookup back from Talos, and it's going to say, this is bad, and you will wind up with a security event on FMC. Another pathway is with a known file. Again, this starts out with secure email data, right? We find that the file is malicious because we processed the URLs and we fully walked the whole path. We know that this thing is bad. On FMC, your starting point is a file policy with malware cloud lookups, right? Deploy the access control policy down to the FTD. FTD observes the file, carves it out, does the cloud lookup. You get your malware event on the FMC. This is really cool stuff, right? Like, I know we're pretty pressed for time, but this is, this is how we leverage telemetry coming out of one product for the benefit of the totality of the ecosystem, even if you're not a secure email customer. So, any questions?
I have a question regarding Eve.
Yeah.
We're not currently utilizing it, and I want to enable it. Is it a monitor mode? I know you talked about how we can set the threshold.
Yes. Yeah, there's a monitor mode, which is what's on by default when you first switch it on. It will log all the bad stuff it catches too still, but it would just be something you'd want to periodically check your security intelligence events to see if you need to remediate a host. You want to do that either way, right? Even if it's blocking, if you block a C2, you still have an infection on your host.
And a follow-up question, if it does block, it's going to show the connection event.
Yep.
It's going to reference Eve.
Yes, it will show the reason. I believe just says encrypted visibility or something along those lines. Yep.
You have to
Yep.
snort me now.
Yeah.
Here you go.
There you go.
All right, so sorry, I skipped ahead the one slide there, but just a quick recap. We got 90 seconds, let's do it. We have the scaling problem. If I can go back, come on. The visibility problem with TLS, this is where Eve comes in. Eve is the on-box Bayesian classifier, fed big data sets, and can tell for HTTP, HTTPS, quick, stun, SSH. If something is malicious or not on the way in, it gives it a threat confidence score. We have the scaling problem with exploits where SnortML comes in, and we've trained it on entire classes of vulnerabilities, hopefully with more to come soon. But today, SQL injection, command injection, cross-site scripting. We have the malware scaling problem. So we take the samples, run them through different models, and come out with concise static coverage in the form of ClamAV signatures. We have the scaling problem with web categorization. There are way too many internet sites online to visit them all. And so we use our WebCat tool, now in its 3rd generation, to provide coverage for that. And then the scaling problem with phishing, which was a whole big bunch of stuff that we do there to do different types of dispositions for everything fed in from secure email, but our entire ecosystem that does lookups benefits from. So, I know we're out of time here. This clicker does not like me.
Yeah.
Don't forget to tip your bartenders. Please leave us a review. This is our 2nd time at Cisco Live US. We would love any feedback. Hopefully next year we'll have even more things to share, because this is not the end state of our machine learning journey at Cisco. So we appreciate you joining with us. Please stay connected. TalosIntelligence.com is great. They have a great blog. We have beers with Talos if you like your podcast. Great for the plane ride home. Please complete your session evaluations, know how we can do better next, help us know how we can do better next time, and go hit all the different areas of Cisco Live while you still got a couple days left. And thank you very much.
Thank you, guys.
Appreciate it.